Okay, so in this section, we're going to be going over section 2.1, which concerns direction fields and equilibria. And it's okay that those words don't mean anything to you yet. They're what we're going to be learning in this section. And I went ahead and wrote down the goals for what we're going to be learning before starting recording because I thought mostly you're just listening to me here. So I didn't want you to be waiting up on me writing. But I'm going to point at stuff and draw squiggly underlines as I say it because I don't know if pointing actually works here. So our goals are to, first of all, learn about what is a direction field. And so that's going to kind of come down to two different things. First of all, we're going to learn how to create one for a differential equation. That's kind of a more graphical task. And then we're going to learn how to read one to find solutions. And so that's more about interpretation and understanding what they actually mean. After we go over direction fields, we'll move on over to equilibria. There are different ways to explore kind of similar ideas. And so we're going to be finding equilibria or something called critical points. Those are just two different words for the same thing. I'll usually say equilibria, I think, just because I like that word. And this will also be broken up into two different things. One that's a bit more computational, how to find equilibrium values and classify them. It's very much like an algebraic type of problem. And then after that, we'll talk about what equilibrium values actually mean for solution behavior, more interpreting the results of what we did when we first learned what equilibria were. So both of these tools that we're learning are important for understanding the behavior of differential equations. So these are useful because they tell you about ODEs before you solve them. And so most of this class is going to concern solving differential equations, but most differential equations can't be solved the way that you'll learn to in this class. And so these tools that we learn at the start, even though I think when you take this class, you feel like they end up not being so useful because you learn how to actually solve differential equations. So why would you need these things? In reality, they're very helpful because we look at a very small class of differential equations here, but these types of tools would carry you through many more than that. So jumping right into that first topic, direction fields. The first thing we're going to do is define them. And it's going to be a lot of words to define them because direction fields are a graphical tool and it's hard to talk about them in words. So if this next slide doesn't make much sense to you, that's okay. Just like take in the words and then try to connect it with the example we'll do afterwards. But a direction field is a plot in the XY plane that demonstrates the behavior of solutions to the differential equation dy dx is equal to f of xy. So it's kind of a way that we just graph solutions to differential equations without solving them. And the way we do that is we create this field using a bunch of tiny arrows. At every point on the graph. And the way those arrows are helpful to us is because each of them has slope f of x0, y0. Each of them has slope that's given by that differential equation. And so what happens is once you draw those arrows, they're going to indicate the direction of a solution from any point. And we'll do an example that makes this more concrete in a second. But basically, a differential equation, we learned last class, describes how a dependent variable, here y, changes depending on its independent variable x. And these arrows are going to kind of point out that change and give us a way to follow along where the solution might go, even if we don't know what it is. And to try and make that kind of clearer, we're going to look at this differential equation. dy dx equal to 0.2 xy. The 0.2 isn't going to matter a whole lot for us. And before we actually do the problem, let's kind of relate back the definition to where we're at. I told you this f of xy was going to be important because we're going to plug in a bunch of points x0, y0 and evaluate its slope using that f of xy. So here, the f of xy is that thing that's equal to dy dx. So we've got f of xy is equal to 0.2 xy in terms of the notation on the previous slide. And what I want to do is evaluate it at a bunch of points, x0, y0. That's what I said on the previous slide is what's going to make the direction field. So I'm going to have this xy plane. There's all these points, x0, y0, everywhere where I want to know what the slope does. And so to populate this field, which let's try to make that a little bit straighter, I guess. There we go. There, that's as good as it's getting. To populate this field, I just need to figure out what 0.2 xy does everywhere in this plot. And so how does 0.2 xy behave? What does it do for different values of x and y? So if x and y are both positive, we know that 0.2 xy is going to be positive. And if x and y are both negative, 0.2 xy will still be positive. If they have opposite signs, then their product will be negative. So what that's telling me is if I'm in this quadrant where x and y are both positive, then 0.2 xy is positive. Something that has slope 0.2 xy will point kind of up. Similarly, if x and y are both negative, then x times y is positive, and so the slopes that I get from computing 0.2 xy will point up. And then in the other quadrants, they'll point downwards. So that's something that I learned just from that information right there. I'd also like to know kind of how steep a slope is. So I know that I should have positive slopes in this region right here, but you know, positive slope could be this, could be this, it could be this, it could be this, it could be any of those things. So we need to kind of like narrow down the magnitude of the slope based on what values x and y take on. So if x equals 0 or y equals 0, I know that 0.2 xy is equal to 0. Otherwise, 0.2 xy increases with the magnitude of xy. So together, those two things mean that my slope is 0 for x and y equals 0 and increases with xy magnitude. The further I get from x or y equal to 0, whether that number is positive or negative. So I'm going to stop here because it's been 10 minutes. In the next video, we'll actually take all these different rules that we came up with and draw them on this plot and then see what that tells us.